So unless I give a prior announcement, we will have our class as per our schedule. Okay, as per our normal schedule. Uh, 4 of you have joined. Let us just wait for 2 minutes because there are 9 of you, and we will start in a few minutes. Let's just wait for 2 minutes. Okay, I think we can start. It's very unfortunate. Only 4 students have joined the class. We didn't have any class or what today? We were supposed to have other classes also. So it's partly on the teacher's fault also. I don't think anyone has conducted their class today yet. So who were supposed to have class in the morning? Zosang is supposed to have class. Raghu is also supposed to have class. They are not having class or what? Can someone respond? Did you have any class in the morning? You were supposed to have 2 classes before me.
No, sir.
No. Yeah.
So this was the first class, sir.
Pardon? This was the first class. This is the first class.
Yes, sir.
Yeah,
Yes,
but
sir.
I think we really need to have a departmental meeting or some sort, because if we are not taking class, then at least we should have a prior announcement. Did they have any announcement that they are not going to have class?
No, sir. There was no announcement for today, sir.
Yeah, that's not good. That's quite irresponsible on our part. Last week and the previous week, I didn't take proper class because I knew that you were involved in some sort of, I don't know, some of those of you who are here, they were involved in some sort of field work and all. But from this week onwards, we are supposed to have regular class. We have to discuss in the departmental meeting. Okay. So since I'm the first class, probably some of your friends might have already gone for other works, maybe thinking that classes will not be conducted. But practicals, I cannot start it right now. Practical, once I finish the undergraduate practical course, I will start practical course also. But let us finish the theory part first, and then we can move on to practical. Just 1 minute. Okay, I think I can start. Now, today we will continue our discussion on characteristics of operation amplifier. Here, another characteristics which we are going to discuss is called common mode rejection ratio. See, as I already mentioned earlier, op-amp is differential amplifier. Where is that? Yeah, point number one, the characteristics number one. Yeah, op-amp is a difference voltage amplifier. So it will take the difference in voltage at the two input terminals, V1 and V2. What is V1? V1 is the non-inverting input, which is usually connected to pin number 3, not usually, which is always connected to pin number 3, parts identification number 3. V2 is called the V2 is called the inverting input, which is connected to part identification number, pin number 2. Okay, and op-amp, what it will do is it will amplify the difference in voltage at pin number 3 and pin number 2. The difference in voltage supplied at pin number 3 and pin number 2. All right. So like here, as I've shown you before, these are the pin number 2, pin number 3, and all. And output is taken from pin number 6, which is from behind in this picture. So whatever voltage which is detected or captured at pin number 2 and pin number 3, voltage captured at pin number 2 is denoted as V2, voltage captured at pin number 3 is denoted as V1. So the difference voltage is VD is equal to V1 minus V2. Output voltage will be your gain. Here we refer to this as an open loop. Open loop means you are not connecting feedback circuit. So there are certain other circuits like when you connect the output voltage signal to the input terminal, that is called the feedback circuit. So when you have a feedback circuit, the gain of the amplifier under such feedback circuit is called open loop gain. All right, the gain of the amplifier, the gain of the amplifier under such feedback circuit or in the presence of feedback circuit is called closed loop gain, closed loop. Okay, now when you do not have any feedback circuit, you are simply supplying input signal to pin number 2 and pin number 3 here, and you are taking the output from pin number 6. Then in that case, the gain of the amplifier is called open loop gain. So the gain of the amplifier in such cases usually denoted as open loop gain, AOL, open loop gain. Okay, AOL. Now, when voltage signals are received at pin number 2 and pin number 3, the difference in voltage is amplified like this with this open loop gain, AOL. So the gain, open loop gain 4741 is, as I mentioned earlier yesterday, day before yesterday, it was 200,000. Okay, open loop gain is 200,000. Now, see, when you use this integrated circuit in maybe in audio amplifier or maybe in some other purpose, some other instruments or equipments, there it is possible that there can be certain electrical noises like small black voltage fluctuation or small electromagnetic pulse and all. So or small voltage fluctuation here and there. It is possible that such noisy signal can be captured at pin number 2 and pin number 3. Okay, so in the presence of certain environment, when you fabricate this IC741 in a electronic circuit boards, and in such electronic circuit board there will be certain transistors, resistors, capacitors, and all those things. So it is possible that in such circuit there can be some undesired noise. So if there is an undesired noise, such undesired noise may be unintentionally supplied to pin number 2 and pin number 3. So when undesired noise are supplied to pin number 2 and pin number 3, if that causes this difference voltage, which is V1 minus V2, it can alter the output, like undesired alteration or undesired modification of the output can happen, right? But the design of this op-amp is that it is a difference voltage amplifier. So suppose you have a certain uniform undesired noise around this pin number 2 and pin number 3. Such noise can be picked up or can be received at pin number 2 and pin number 3 simultaneously. They will be received at pin number 2 and pin number 3 simultaneously, right? So if such noise is received at pin number 2 and pin number 3, since op-amp amplifies only the difference voltage, the noise contribution to V1 and the noise contribution to V2, they will cancel each other. When they cancel each other, then the output voltage will not be affected. Let me put it this way. So when you are using this IC741 in an electronic circuit board, there is a possibility that there will be undesired noise in a large electronic circuit board. When such undesired noise is also there, this op-amp, as it amplifies only the difference voltage, so if those undesired noise is received at pin number 2 and pin number 3, or those noise modifies V1 and V2 here, usually in such noise environment, the noise signal received at pin number 2 and pin number 3, which is adjacent to each other, are equal. So such undesired noise will cancel each other out, and it will not contribute to V naught here, because V naught this op-amp will only amplify the difference voltage, right? So equal amount of undesired noise, if received at pin number 2 and pin number 3, they will be nullified, and the capacity or the property of operational amplifier to reject such kind of noise, is called common mode rejection ratio. Okay. Now, as I said, like here, so suppose you connect pin number 2 and pin number 3 to a common signal terminal here, a common noisy signal terminal here, like shown in the figure here, VCM, we call it common mode voltage. So if you supply equal amount of voltage here, your VD is supposed to be 0. All right, if VD is 0, then you do not have any output voltage. Your output voltage will be 0 because of the formula here, that output voltage is open loop gain into VD here. So the gain of the amplifier, when you connect pin number 2 and pin number 3 to the same terminal or the same voltage signal, is called common mode gain, CM. Okay, ACM, common mode gain. Since output voltage is 0 under common mode configuration, ideally, right, for ideal op-amp, if same signal is received at pin number 2 and pin number 3, output voltage will have to be 0. So for ideal op-amp, V naught is 0 under common mode when you connect to common terminal. Therefore, your common mode gain SCM is also 0 for ideal op-amp. Common mode gain SCM is also 0 for ideal op-amp. And open loop gain of an amplifier, standard open loop gain, as I said before, it is a 200,000. Now, for ideal op-amp, the common mode rejection ratio is defined as the ratio of open loop gain to common mode gain. Now, for ideal op-amp, what will be a CMRR value? For ideal op-amp, CMRR value will be something like 200,000 divided by common mode gain is 0, right? So for ideal op-amp, common mode rejection ratio is infinity. Common mode rejection ratio is infinity. So it will be able to, for ideal op-amp, it will be able to reject any common mode noises received at pin number 2 and pin number 3. Any unwanted noise received at pin number 2 and pin number 3 will be rejected for the fact that op-amp amplifies only the difference in voltage at the two input terminals. Okay, so for ideal op-amp, as you see from this calculation, see, we have worked out this calculation. For ideal op-amp, output voltage has to be 0 when you connect the two input terminals to the same signal, which you call it common mode voltage, or which can be your unwanted noise signal. And your if V naught is 0, then your common mode gain is 0. Common mode gains ACM is the gain of the op-amp when you connect the two input terminals to the same common terminal, ACM, right? So if ACM is 0, AOL, open loop gain is 200,000, then your ideal op-amp CMRR will have to be infinity. Now, another characteristics we are going to discuss is called slew rate. Slew rate means slew rate of an op-amp is actually how quickly the op-amp circuit can respond to any changes at the input terminal. Say this op-amp, I have shown you the complete circuit diagram or internal circuit diagram of an op-amp, right? Here I think I can show you again in the circuit in the slides I still have. Yeah, this is the circuit. So when you are supplying input to pin number 2 and pin number 3, they are connected to the base of the NPN transistors here, and you see that there is a network of transistors and resistors here in this internal circuit of op-amp IC741. And usually in order to respond in the output terminal here, pin number 6 here, you can see pin number 6 here, right? In order to respond to any changes in the input terminal here, because of the large network of transistors and all these resistors and capacitors here, there can be a delay in the response at the output section. Even if you have certain changes in the input section, there can be certain delay in order to respond to the input terminal changes here, right? So the delay in the output signal when there is a alteration or when there is a changes in the input signal is usually an issue, right? So slew rate is a measure of that, how quickly output of an op-amp can respond to any changes at the input terminal. That is what is defined by a slew rate. So for ideal op-amps, for an ideal op-amp, suppose you have input voltages, let's say 0 here, and suppose you suddenly jump to, let's say, 1 volt here, for example, 0 volt to 1 volt. Ideally, output voltage, let's say this is V in, let's say this is V naught. Ideally, output voltage should also promptly respond to changes in the input. Okay, ideal op-amp should also output voltage should also promptly respond to any changes in the input here. So that means what I can say here is that the slew rate has to be infinity. Slew rate has to be infinity. Slew rate infinity means simultaneously, that is within 0 second, if the input changes is reflected in the output voltage here, output signal here, within 0 second, then we can say that your frequency response or the response of your op-amp under such condition is very, very good, right? So for an ideal op-amp, within 0 second itself, it should immediately respond to any changes in the input. The output terminal should immediately respond to any changes in the input. So that means in the slew rate of an ideal op-amp is infinity. Okay. But for practical op-amp, the slew rate is 0.5 volt per microsecond. So what it means is that if there is a change in the input signal here, something like this, it jumps directly like this. Output of an op-amp can change by 0.5 volt within 1 microsecond. Within 1 microsecond, it can sieve the value by 0.5 volt only. So within 2 microsecond, output signal can changes by 1 volt. Within 3 microsecond, output signal can respond or can vary its voltage by 1.5 volt. So that shows that there is a slight delay here in the output section, in the output voltage, in its response to changes in the input here. Okay, so there is always a slight delay, something like this, like the curve or the graph are shown here in the screen. So that is some issue with op-amp you have to remember. Now another point is the frequency bandwidth of an ideal op-amp. Frequency bandwidth means bandwidth of an amplifier. It tells us that within which frequency range the gain will be uniform. Okay, within which frequency range the gain will be constant or uniform. So usually RC couple amplifier, for undergrad physics student, we have studied RC couple amplifier. Just 1 minute, somebody's calling. Oh, hello. Yes. Oh, yeah. Oh. Ingin ta lal RC. Ingin ta swero ingin ta lal RC. Class ka ni mega. Oh. Oh, online class zone ko lela. Oh, okay. Kasi utra pa mo 15-20 minutes. Oh, no. So in an RC couple amplifier, which we have studied in the undergrad physics course, we have seen that the gain of, when you plot gain versus frequency here, gain versus frequency curve, the gain of the amplifier is uniform within 20 hertz to 20 kilohertz. So it's something like this. Gain of the amplifier is more or less uniform within this range. Okay. So that shows that RC couple amplifier can be used for audio amplifier, because human audible range is between 20 to 20 kilohertz, more or less. Okay, so if you use it for an audio amplification for a low frequency, also the gain is same as signal at a high frequency. Also there will be a uniform amplification of your audio signal in RC couple amplifier. But if the gain is not uniform like this, there is another amplifier called transformer coupled amplifier also. Transformer coupled amplifier also. It has a very irregular gain structure, something like this. Transformer coupled amplifier. So what it means is that this particular frequency, let's say this particular frequency is, let's say 800 hertz. 800 hertz has a very high gain here. However, this frequency, let's say 10 kilohertz. 10 kilohertz has a very low gain. So when you use it for, let's say, audio amplification, this transformer coupled amplifier, this 800 hertz signal will be heavily amplified. It will be very loud. But when you have an audio signal which is having around 10 kilohertz, the amplification or the gain for such signal is quite low here. The gain for such signal is quite low here. So if that is the case, this 10 kilohertz signal, after this amplification process, if you feed it to your audio speaker, the sound will be, very low and will be very difficult to hear, isn't it? However, 800 hertz signal, it will become very, very loud if you feed this signal to your audio speaker. So for many applications, we require an amplifier which performs uniform gain over a large frequency range. Okay, so that's why we need an amplifier with a large frequency bandwidth. So the bandwidth we talk about is, the bandwidth means the range of frequency within which the gain is more or less uniform. So as I said before, RC coupled amplifier has a bandwidth from 20 hertz minus 20 kilohertz minus 20 hertz. So within this range, it has more or less uniform gain, right? But this operational amplifier performs much better than RC coupled amplifier again in terms of this frequency bandwidth. The frequency bandwidth of an ideal op-amp is infinity. For practical IC741, the frequency bandwidth is 1 megahertz. So here, as you see, RC amplifier has a bandwidth of around 20 kilohertz. However, op-amp has a bandwidth of 1 megahertz. So within a very large frequency range, it will give you uniform gain. So the signal will be uniformly amplified. Now, this is a circuit for an application of op-amp as a voltage level detector. Application of op-amp as a voltage level detector. Now, let's say this is your op-amp. Wait, yeah, this is your op-amp shown here in the figure. Pin number 2 is your inverting input. Inverting input, we call it V2, right? Pin number 3 is your non-inverting input. We call it V1, non-inverting input. So as I said before, op-amp is a difference voltage amplifier, AVD. What is your VD? VD is V1 minus V2. Now, output is taken from, oops, this is wrong. This is pin number 6. This is pin number 7. Okay. Output is taken from pin number 6. Now, if you connect certain reference voltage to pin number 2, so let's say a certain reference voltage is connected to pin number 2. V2 is reference voltage. Okay, it could be 1 volt, it could be 2 volt, or whatever reference voltage you choose it to be. Now, if you supply input signal here, sinusoidal signal to V1, V1 is equal to V in. Here you are supplying a certain sinusoidal signal to pin number 3, that is your V1 is equal to V in. So therefore, under such condition, your output voltage will be equal to open loop gain A into V in minus V1 volt. Let's say your reference voltage given here is 1 volt. Yeah, reference voltage is 1 volt. So V in minus 1 volt. So your input signal, input voltage, if you plot it, for your V2, you have a reference voltage which is 1 volt given by the dotted line here. For your V in or your V1, V1 is actually your V in, right? For your V1, you have a sinusoidal signal like this. Now, let's say between this interval, small interval, as I identified here in the picture here, within a small segment here, small interval. Okay, within this small interval, you will find that VD, which is V in minus 1 volt, is negative. Okay, within this small interval, your VD, difference voltage, which is V in minus 1 volt, is negative. How is that? Because within this interval from here to here, this is your V in. Okay, this is V1 is equal to V in. This is V2 is equal to reference voltage. Your reference voltage is fixed at 1 volt. So within this interval here, V in sinusoidal signal is rising from 0 to this. So V in is less than reference voltage. If V in is less than reference voltage, your VD will be negative. If your VD is negative, your output voltage will be open loop gain is 200,000 multiplied by certain negative value. If you multiply it with certain negative value, it will go to negative saturation. Negative saturation. So yesterday I mentioned that why it goes to the negative saturation, day before yesterday. Thing is that here your plus VCC is plus 15 volt, minus VCC is minus of 15 volt. So these are the DC power you are giving to your op-amp. For the transistors within your op-amp to operate, you are giving this DC energy. Okay, so out of this instrument or your op-amp circuit, you cannot extract any electrical signal or electrical power greater than plus 15 volt or minus 15 volt. So here, even though the gain, open loop gain is 200,000, let's say your difference here is 0.001. Even if this is the case, it will be 2000 still, isn't it? So we cannot go to 2000 volt here because the electrical energy we are giving here between is plus 15 volt and minus 15 volt. So it cannot go to 2000 volt here. The output signal cannot go to that. Okay. So because of that, it will saturate to a certain negative value, which is slightly below 15 volt, minus 15 volt. Maybe it will saturate at minus 14 volt. Positive saturation will be at plus 14 volt. Okay. So here it goes to negative saturation here. Output signal goes to negative saturation here. Corresponding to this segment here, it goes to positive negative saturation. Now, if you look at this range here, between this range, if you look at between these two range, in this range, you will see that your input signal here is going up like this and going down like this. And if this is your reference voltage. Within this range, you will find that VD is positive. Okay. Within this range, VD will be positive, isn't it? Because V in is greater than 1 volt within this range. VD is positive. If VD is positive, then whatever the output signal will be, open loop gain 200,000 multiplied with certain positive value. So it will tend to jump to a very large positive signal, but because of the limitation provided here at the DC power of plus 15 volt, it cannot go beyond that. So it will go to positive saturation, which is around plus 14 volt. Positive saturation, which is around plus 14 volt. Okay, so within this interval, it goes to plus 14 volt, positive saturation. Now, between this interval, if you look at the op-amp again, between this interval, your V in or V1 is this, isn't it? Your V1 or V in is like going like this. So between this interval, your V in is less than 1 volt. V in is less than the reference voltage, right? So if V in is less than the reference voltage between this interval, then your output, your VD will become negative again. If your VD is negative again, your output voltage will again go to negative saturation. So between this interval here to here, it goes to negative saturation, negative V set. And again, between this interval here, V in is greater than 1 volt. So as long as V in is greater than 1 volt, because of the large gain of 200,000, it will go to positive saturation again between this interval. It goes to positive saturation again, like this. Okay. So that is how this op-amp in an open loop configuration will operate. So this is called zero crossing detector again. Op-amp zero crossing detector. Here if you connect your reference voltage, your zero, if you connect your non-inverting input, this is called pin number 3 is called non-inverting. You have to be familiar with all these terms by now. Pin number 2 is called inverting. Yeah. So when you supply your signal V into pin number 2 and you are connecting your reference voltage to pin number 3, what is your VD? VD is V1 minus V2. V1 is the voltage supplied at pin number 3, that is V1 is equal to reference voltage. V2 is equal to your voltage supplied at pin number 2, which is your V in. Okay, V1 is 0 volt. Here you see that V2 is V in. So if this is the case, V1 is 0, V2 is equal to V in. So your VD is negative of V in. Difference voltage is negative of V in here in this case. Okay. Now, let's say you supply a sinusoidal signal as the input here. This is your V in. Sinusoidal signal like this. Now, if you are going to trace the output here, look at this, the output. This is your output, V out. Between this to this, within this interval 0 to, this is called pi, you know, 0 to pi. Between 0 to pi, when your V in is positive, V in is positive, your VD here, for a positive V in, VD will be negative, isn't it? For a positive V in here, between 0 to pi, this is a positive signal of an AC. Between this terminal, between this interval 0 to pi here, when V in is positive, your VD will be negative if you look at this formula. If VD is negative, then your output will be 200,000 multiplied with certain negative value. That means your output voltage will go to negative saturation. So between 0 to pi, output voltage goes to negative saturation here. Now, in this interval, that is from pi to 2 pi here, your V in signal, if you look at this, this is in the negative pulse. V in is now negative. If V in is negative, if you look at this formula now, VD will be positive. Negative V in means minus into minus positive. VD is positive. Okay. So if VD is positive, difference voltage is positive, then again your output voltage will be 200,000 multiplied with certain positive value. 200,000 multiplied with certain positive value. So that will go to positive saturation again. Okay, it goes to positive saturation. So again, 2 pi to 3 pi, your V in is positive. So looking at this formula,